the last class we were discussing about this particular numerical. I gave that okay, so a negative feedback control system which is characterized by so and so, that is g of s equal to k divided by s into s plus alpha and h of s equal to 1. So this is the thing what we have learnt, what we have taken the last class. So for this particular numerical, we have to find the values of k and alpha, so that mr will be equal to 1.04 and omega r will be equal to 11.55 radians per second. So and think that the second part of the question is for the values of k and alpha, which we have found are formed in the part A. Calculate the settling time and bandwidth of the system. This is the question they have asked. So, but this question is in the terms of what you call for that frequency domain. So here for that also we need to calculate the system characteristic equation is given by 1 plus k divided by s into s plus alpha will be equal to 0. So we get the characteristic equation as s square plus alpha s plus k equal to 0. Okay, so after that in the last class we did this also, comparing the above equation with the reference characteristic equation, that is s square plus 2 delta omega n into s plus omega n square equal to 0. So we will get like a 2 delta omega n will be equal to alpha and omega n square equal to k. So this is the thing what we get. Okay, so I think everybody got this particular answer correct. Up to this stage you have all learned in the last class, isn't it so? Is it not so?
Yes, sir.
Okay. So once we do this particular process, okay, once we have found this one,
Yes,
so we
sir.
need to, yeah, we need to take the values like mr equal to what? So mr they have given as 1.04. Okay, mr is what they have given. They have given mr equal to what? 1.04. So once they give the mr equal to 1.04, okay. So we know the formula. What is the formula we know? We know that mr will be equal to 1 divided by 2 delta. So this particular thing you please write it down, all of you. mr will be equal to please write it down. So once you written this one, mr equal to 1 divided by 2 delta into square root of 1 minus delta square equal to 1.04. 1.04 they have given. So now you do the cross multiplication. So once you do the cross multiplication, you do the mathematical things. Okay. So you will get the two values of delta. So on solving this particular equation, so solving process, please do it, all of you. So solving part, you please do it, and you will find the values of delta as delta equal to 0.6 and delta equal to 0.8. Okay. Now the question comes, which value we need to select? Okay. So here we have given that delta should be less than 0.707 because it is something like under damped system only we are going to consider. So delta value, we know that delta should be less than 0.707. So whatever it comes after above the 0.707, we are not going to consider. So here 0.8 is there. So this particular 0.8 is value is above the 0.707. That is why we are discarding this particular value, and delta value we are considering as 0.6. That is why we can say select delta equal to 0.6 because delta value should be less than 0.707. Okay. So once we find out the value of delta, so we can do this particular process. Okay, 2 into delta omega n into 2 into delta omega n will be equal to alpha. So you can find this particular thing that, okay, so yes, for this particular thing, once again we require omega n. So omega r value they have given. So here you can see that in the given numerical, they have given the omega r. Omega r equal to what? 11.55 radians per second. So here that particular 11.55 radians per second will be using. So what is the particular thing we can use? So there is a formula. Omega r will be equal to what? Omega n into square root of 1 minus delta s. So this particular formula, please write it down, all of you. So after we saw the derivations like the time domain, so we would have listed the formulas. Okay, so since we have not listed the formulas, like we have done in the time domain, not a problem. So you can list it in the numerical itself. Okay, so one numerical if you solve, so second numerical it is very easy for you people. Omega n will be omega n into square root of 1 minus 2 delta square will be equal to what? Omega r. Omega r value equal to what? 11.55. So now in this particular numerical, delta value also we have found out. So what is the delta value? 0.6 we have taken. Okay, so 0.6 if you substitute for delta, and omega n value will be arising for 21.8 radians per second. 21.8 radians per second. So just calculate and tell me, all of you. So do it, no problem. You can take your calculator and you do the work, and after you doing the work, you tell me. Doing the calculation part, you tell me. Okay. So can I believe that omega n will be equal to 21.8 radians per second for all the students? How many of you got this particular answer? Please raise your hands. Let us see. Okay. One student has raised the hands. Fine. Good. What about others? Probably they might be doing. So I'll give you 1 minute of time. So please do it and tell me. Okay, so all of you got, I think so. Okay, so now we can go for the next step. So for 2% criteria, there is the time domain specification only you can use it. Okay, so for 2% of criteria, the digital tolerance band. Okay, so here you can see that settling time. Okay, so here why we need to find out this particular TS settling time we need to find out. So in order to find out settling time, yes, anyone want to ask anything? Okay, so we can find out settling time also. So it is 0.305 seconds. It will come. This is 4 divided by delta into omega n. So bandwidth, the formula indicates the bandwidth will be equal to omega n into 1 minus delta square plus square root of 2 minus 4 delta square plus delta to the power of 1 by 2. This is the formula what we have taken. So here you substitute the value of omega n and we substitute the value of delta square, we will get 25 radians per second. Okay. So from this particular omega n and delta value, so we found out that what is the value of k and alpha. So you can use this particular things. So in order to calculate the bandwidth. So write it down all of you. So while writing this particular step, you'll understand what is the formula also, as well as the how to solve the numerical also. Why? Because so 99% they will not ask you to derive the frequency domain specifications. Okay, that is not there. So only direct equations you need to take it. So the just in a comparison. So for you to understand, I just showed that how the derivation part, how the understanding part will be there in the last classes. So you can able to take this particular thing. So complete it all of you. So once you complete this, please let me know. Hope all of you have taken this one. Okay, so we'll go to the. Okay, so only one numerical we have done. Okay, so far why? Because this is not so important. So here what exactly is happening is so compensation techniques. So here compensators are used. So here next topic, you please take down all of you. There is a next topic called about compensation techniques. Okay. So in the module number 4, volume thing. So just brief out what are the things we have studied and what are the contents are there. So root locus is there. So we have seen the root locus techniques, and we have seen 4 numericals, how to plot the root locus also, and how to find the stability. Next thing is what RH criteria, that is roots Hurwitz criteria. So there also how to find out stability using the RH array. So we have seen the procedure, we have seen the difficulties in that, and we have seen the numerical related to that also. Clear? That is the second thing. Third thing is what frequency domain analysis. That means what just a comparison. So there are some equations which with respect to the time and resolutions. So time domain specification equations. So all those things we have studied now. Okay. Also, so if anything was asked, okay, so question. So like how you solve in the time domain, so same thing you apply here also. You can get the frequency domain analysis also. That is the thing. Next topic is what compensation techniques. After that, Bode plot is there. Bode plot, when it completes, your syllabus will be completed. So compensation technique, we will take just a theoretical part. So what is the theoretical part? We are going to discuss that now. So when talking about the compensation techniques, so compensators are used to improve the transient response of the system. So here compensators that use pure integration for improving the steady state error, or pure differentiation for improving transient response are called as what ideal compensators. Here compensators are used to improve the transient response of the system. So now here when the compensators are used, okay, so compensators are made up of pure integration or pure differentiators, integrators or differentiators. Okay, so when it is only the purely integrators or purely differentiators. So when that particular things we are using, those are called what ideal compensators. Ideal compensators. So there these ideal compensators can be realized by using active networks. So which in case of electrical networks, these require use of active amplifiers and additional power sources. So these ideal compensator can be realized by using the active networks. So which in case electrical networks, see active network means what? Only the electrical networks only we are going to use. Okay, so where the power is available. So here in electrical networks, these use the active amplifiers additional with the power sources which are required. So when you're talking about the other design techniques that avoid active devices for compensators are called practical compensators. Okay, so now here a practical compensator means what? That we are going to generate the compensator technique, compensator circuits with by the use of passive elements. So your resistor, if you take, okay, resistor is a passive element. Okay, once you connect the input and output and power supply, then only it will work. Else it is not going to work. That is called what? Passive resistor. Not a passive resistor. Resistor, it is a passive component. Capacitor is also a passive component. So by using these particular things like resistors and capacitor, okay, by using that particular resistors and capacitors, so we can build bottom full count. Okay, so here and the main disadvantage of a passive compensator network is that steady state error is not driven to zero. So when you're talking about ideal means what? It will be the whatever the errors you talk, so that particular errors will become zero. So error free, we say. But when you're talking about the practical, so in the practical network, so error will not be equal to zero. Error cannot be equal to zero also. That is the one thing we need to understand. Okay. That is the difference between practical compensators and ideal compensators. Ideal compensators are made of active devices. Practical compensators are made up of passive components. What are the passive components? Resistors as well as capacitors are the passive components. So what is the difference? The steady state what is there, that error will not become zero. Oh, sorry, when you're talking about the practical compensators, so error will be equal to zero when you're talking about the active components. So your simple electrical network with resistors and capacitors as elements are classified as lead, lag and lead lag networks. So this is the very important thing. Lead, take the ID. So lead, lag networks. So what do you mean by lead? Lead means what? When you want to increase the phase signal, you are going to increase the phase of the signal. Then we are going to use the lead network. So that the lead compensation, that means what? Sometimes due to some problems in the network, so the angle the phase of the angle is getting reduced. So at that time, if we are using the lead network, the phase will be increased. So when the phase is getting increased, we are going to compensate, because compensating for the loss. And lag also, sometimes if it is the very high phase, so we want to reduce it. So in order to compensate that particular very high, we are going to use lag. So the combination of these two is called lead lag networks. So I can write this particular circuit diagram, all of you. So you can see that lead compensator and its characteristics. This is since as I told you, it is a theoretical part. We need to understand the circuit and we need to understand some of the concepts here. Okay, please take this particular diagram, the circuit diagram, all of you. So once you take this particular circuit diagram, please let me know. So I can see this in the diagram. There are two networks. Okay, one is in time domain, one is what? In the Laplace domain. So in the Laplace domain and time domain, you can see that. Okay. So here Vi of t is the input, V naught of t is the output. The Laplace domain, it is Vi of s and V naught of s. Okay. So here R1, C1, R2. Okay. So here also R1, R2, and when we are talking about C1, it will be 1 by S into C1. This is a Laplace domain how we are going to represent. So you can see that there is a input Vi of t. So it is going through the R1. Okay. So here there is a parallel, there is a resistance, and to the parallel to the resistance there is a capacitance also. So when this particular configuration is there, it's called as lead compensator network. Hope all of you taken. So here you can just write down. Okay, see, since there is no derivation part for you people, so no need of understanding the derivation. Keep it very simple. Remember this equation, that's all. Okay, so the transfer function of first order compensator is given by, okay, so GC of S, that is GC of S is general equation. Okay, so gain C means compensator of S. GC of S equal to K into S plus Z divided by S plus P. So here what is S plus Z? Z indicates 0 and P indicates pole. So it is the first order. Why it is first order? Because the denominator power of S is 1. Okay. So now take this particular equation. Okay, once you take this particular equation, the objective of the design is to select Z, P and K. So now here objective of the design is to select z comma p comma k. Why? Because in this particular equation you can able to see that k is unknown, z is unknown, and p is also unknown. So if you select this particular values of k, z, and p properly, then we can able to achieve the compensation properly. That is what exactly the concept here. Okay, the objective of the design is to select z, p, and k in order to provide a suitable performance. Fine. So yeah, when z, okay, so in this particular choosing also, there may be some conditions like when the modulus of z is less than modulus of p. That means what? The value of z is less than value of p. The network is called as what? Phase lead network, and as a pole zero diagram. Okay, so here in order to achieve that particular phase lead, so they have found out that the modulus of z should be less than modulus of p, then only phase lead will happen. So if it in the other way, that means what? If z is greater than the p, so phase lead is not going to happen. Okay, so that is why you can see that in the pole diagram, see when they explain diagram, when you are drawing this particular diagram, you can able to see that. So in the explain, so z is coming first. That means what? The value of z is higher than the value of p. Okay, so that is what exactly the meaning. So here modulus of, see, -2 and -5, which is greater? -2 is greater. But if you take the modulus of it, 2 -2 modulus is 2, -5 modulus is 5. So which is greater? 5 is greater. So obviously, when you're talking about the modulus, the value of z should be less. That is what exactly the concept here. Okay. So in other words, I can say that when you're plotting the pole zero diagram in the explain, so I can say that it will be minus z. So that means what? Minus z, the value of z should be higher than the p. Okay, so for that simplicity, we have taken that modulus of z should be less than modulus of p. So when this particular value is happening, then I can say that, okay, phase lead is going to happen. So please write this particular equation. Once it is done, please let me know. I think you've taken the network, so please take this particular sentences. So this particular phase lead lag network, there will be a 6 marks question. They will be asking couple of times. So that means what? Oftenly. Okay, so out of 2 times, 1 time will be there. This question for 6 to 8 marks. They will ask you that to explain phase lead lag and lead lag network, or else they will ask you that explain the compensation networks. Okay, like that they will be asking you question. So at that particular time you need to answer. So once you're done with it, we can plot the pole zero diagram. So according to the concept, according to the definition, I can say that the z value should be p value. Minus z will come minus. For example, I'm telling -2, so -5. So obviously -2 for z and -2 for p. So it will come near to the origin. Okay, the value of z should be greater. And taking the modulus, it should be lesser. Take this particular split. So next we'll see that if the pole is very much away from the origin, so if the pole is very much away from the origin, so that is when P is very much greater than Z. Okay, so then the 0 occurred at the origin of S plane. So we would have the differentiator having the transfer function GC of S will be equal to K divided by P to the power of S. So that means what? If the pole, let us consider like when the pole value is around 15, okay, so minus 15 is the K plus 26, let us consider. So 26 is the plane. So and if the 0 is at origin, okay, the 0 is at origin, what is the value 0 at origin is what? K S plus 0. So S plus 0 is there, no? So then I can say that, okay, so we can have the formula, reduced formula, that is K divided by S, K divided by P into S. So K is the gain value. So S plus 0 is we have taken, okay. So in the bottom also it will be considered as K divided by P into S. So we are going to reduce the formula. So what is our condition? The P must be very much greater than Z. Then the equation will be reduced to, okay, we'll have the differentiator equation, will be having the transfer function GC of S will be equal to K divided by P into S. So this is the equation. So now for this particular what do you call for that circuit, okay, so if you just for the circuit we are writing the equation for the input and output, that is transfer function. The transfer function G1 of S will be equal to V0 of S divided by Vi of S. Okay, the transfer function G1 of S will be equal to G0 of S divided by Vi of S. So for the lead network, which is shown in the figure B, there is in the Laplace transform, okay, Laplace domain. So now by using the principle of voltage division, so GC of S divided by equal to V0 of S divided by Vi of S will be equal to Z2 divided by Z1 plus Z2. That means what? R2. So we have taken the R. Okay, instead of Z, you can make it so that R2 divided by R1 plus R2. Okay, so where R1. Okay, so when R1 will be equal to what? R2 will be equal to Z2, I can say, and Z1 I can say that is, okay, R1 divided by 1 plus S into 1. Okay, so they have taken like see here they have taken like the what do you call for that the resistance. Okay, so equivalent resistance for this particular nodes to between two elements, and there is the impedance from this particular end. So two impedance they are taken. So Z2 can be equal to R2 directly, whereas Z1 will be equal to what? R1. Okay, so R1 divided by 1 plus S into C1 into R1. So this is the equation, equivalent equation, and Z2 equal to R2. So you can use this particular formula. Okay. So this is about our lead compensator network. Okay. So similarly, I will give you the today homework. Okay. So what is the homework I'll give you is write. Okay, write or understand the or explain the lag network and lead lag network. Okay. So can you able to do this particular homework for today and submit tomorrow? So you have to go through any textbook. Okay, so like how I explained the lead compensator, so there will be one diagram for lag compensator. Okay, so here instead of in this horizontal, it will come in a series. Okay, so lead network instead of parallel will come in series, that is lag network. So what is the equation? How to take the equation? how to plot the pole zero net diagram. All those things you must write it down. So that will be called as what homework for you people for today. Is that okay? Can you able to do it?
Yes, sir.
Okay, so do it. Okay, so and one more thing. From next class onwards, I'll start the Bode plots. Okay, so Bode plot. So that Bode plot will be plotted in the semi-log sheets. So that particular process and all I will want to explain you. So you be prepared of semi-log sheet concept. So I will be explaining you people. Okay. So once I explain that particular Bode plot concept, the fourth module will get over. Then the fifth module is very simple and very having the less number of topics we can cover it. Okay. So probably this week and next week also. So we will be completing the model number 4 and we'll be starting the model number 5. Another 1 or 2 weeks, your syllabus will be getting over. Okay. Now I'll give the time. Okay, just those who are not written, please write it down, all of you. Write properly. Can you able to see the screen? Can you able to see the screen properly?
Yes, sir.
Okay, okay. Yeah, please write it down. Complete it neatly. So after taking this one, you can go to the down. You can take the equation as well as graph. Once you return this one, you can go through the content, this one, finish it off. Okay, students, I think you will return this one. Okay, so now I'll wind up the class.